Welcome to another exercise on the Simplex algorithm. Here we simply have the exercise. By using the Simplex algorithm, calculate the optimal solution to the following linear problem. Our problem is a classical maximization problem with two decision variables. So we have 2x1 plus 5x2. Additionally, we have the following constraints. 6x1 plus 5x2 should be smaller or equal to 60. 2x1 plus 3x2 should be smaller or equal to 24. And 3x1 plus 6x2 should be smaller or equal to 48. And finally, we have our non-negativity constraints so that both of our decision variables should be larger or equal to 0. With these comments before, we can start to first take this problem in a mathematical notation and transform it into a working table. That is also what I'm going to do first here. So I'm going to copy this problem. Then I'm going to prepare my calculation table. In the calculation table, I'm going to introduce one column per decision variable. So for x1 and for x2. Then I'm going to add one row for the objective function and one row with additional variables x3, 4, and 5 here for the three constraints. So x3 for the first constraint, x4 for the second, and x5 for the third constraint. Since it is maximization problem, I'm going to take the coefficients from the objective function, but I'm going to reverse the sign. So I'm going to switch from plus x1 to minus, from plus 5 to minus 5. I'm going to take these negative coefficients, put them here in the first row, and then I'm going to insert for x1 and x2 0, giving me a function, a value of 0 for the objective function. For each of the constraints, I first have to check whether they are smaller or equal to constraints, which, well, all three of them fulfill. So in this case, I can just take the coefficients as they're given here. So for x1, 6, 2, 3, copy them in the x1 column. And for x2, 5, 3, 6, copy them in the x2 column. For the right side, I can also take the values as is, so 60, 24, and 48, and put them here in this column. So I have the first table already prepared. I also see here on the right that all of these values are positive, so my starting solution is also a feasible solution, and I can directly start with the Simplex algorithm. For this, I'm going to start selecting the pivot column by taking a look at those values in the objective function row. And I'm going to select one column where I have a negative value here, so both would qualify, and where this value is absolutely speaking the largest. So this would be 2, this would be 5. So this column will be pivot column because absolutely speaking minus 5 is larger than minus 2. Pivot column. Now I have to take a look for the pivot row, which of these elements are positive. Well, all three are positive, so all three qualify. So in the next step, what I have to do is take the right-hand value and divide them by these elements. So I'm going to divide 60 by 5, 24 by 3, and 48 by 6. If I'm going to do this, the result will be here 12, 8, and 8. Well, I have to select the pivot element or the pivot row so that these values, which I just calculated, are as small as possible. So in this case, this would give 8, this would give 8. So I can select any of these two columns, rows, sorry, each of these two rows. I'm going to go with 3 because it gives the smaller values. Well, if I do the calculation like this, this will be pivot row, this will be pivot column, so 3 will be my pivot element. If I then recalculate all of this, the place where the pivot element was, I'm going to replace by 1 divided by the pivot element, and all the other values in the pivot row, I'm going to divide by the pivot element. So I have 2 divided by 3, 24 divided by 3, so 2/3 and 8. Everything in the pivot column is divided by minus the pivot element, so by -3. So I have 6 divided by -3 gives -2. 5 divided by -3 is -5/3. And -5 divided by -3 is +5/3. Well, this value is already positive. So next I can check this value, because if this value also gets positive, then I will already be at my optimal solution and I can save some time on calculations. For all these values which are not in pivot row or pivot column, I'm going to use a rectangular form. Rectangular form means I'm going to take a look at this element which I want to change. Consider this as one corner of a rectangle and consider the pivot element as the opposing corner. So in total I would have this rectangle with those two as opposing corners and those two as the other ones. Then I'm going to calculate original element minus these two multiplied divided by the pivot element. So in this particular case, -2 minus 2 times -5 divided by 3. Well, minus gives plus, so -2 plus 10/3, which will in the end result to 4/3. So this value is positive, this value is positive, so I see that I'm already at my optimal solution. Meaning I do not have to calculate all the values in my table. So I do not have to calculate these two, and I do not even would have to calculate these two values if I'm just interested in my values for the decision variables. Well, however, I would have to calculate the value for up here, because this is the value of my objective function. So in this case, if I want to change this value, this would be my rectangle. I would calculate 0 minus -5 times 24 divided by 3. Minus cancel each other out. So I get plus 5 times 24 by 3, which is just 5 times 8, so it's 40. I get to 40 here. Then I'm already done. Well, I have calculated all the other values. So before I go to discuss the optimal solution, let's just have a quick look how I would calculate all the other values. So for 6, this would be my rectangle which I'm going to use. For 3, this would be the rectangle I'm going to use. So 3 minus this times this by this. For 60, this would be the rectangle, so 60 minus 5 times 24 divided by 3. And for this value here, I would have 48 minus 6 times 24 divided by 3. The interesting thing, here I see this gives me a value of 0. This is the reason why before I could select either of those two. If I have this case, one of these will have a value of 0. Well, as I said, this is my optimal solution. So what are the distinct values for the decision variables? Everything which is up here has a value of 0. So x1 is 0. Everything which is here has the values on the right-hand side. So x2 has a value of 8. So my optimal solution is 0, 8. And it gives me an objective function value of 40. Well, with this comment, we solved our exercise. We are at the end of this tutorial. I hope you enjoyed. I say goodbye and see you next time.